Okay, so we just did the coalescent for n equals 2. Now let's do it for n is more than 2. Okay, so we said if we had 2 individuals, then the amount of time we had to wait was on average n generations. But what if we have 3 individuals? Well, again, we're going to ask basically how long do we have to wait until something happens? Because ultimately the tree is going to look something like that, right? So that if we're going back in time, the first event we're waiting for is this first coalescent event. So if we have 3 individuals, then the question is, how does that change the waiting time? Well, when we had 2 individuals, we said that the rate at which they coalesce is 1 over n. Okay, so the rate that these two do is 1 over n. The rate that these two do is also 1 over n. And the rate that these two do is also 1 over n. So if we have 3 individuals in our sample, if we're tracing these 3 individuals, then we're going to have 3 times 1 over n is going to be the rate at which things happen, the rate at which something will happen as we go back in time. And if we have 4, well, if we have 4, it gets a little bit trickier. So now we could have, if we just call these individuals 1, 2, 3, and 4, then we could have 1 and 2, or we could have 1 and 3, or we could have 1 and 4, or we could have 2 and 3, or we could have 2 and 4, or we could have 3 and 4. So that's 6 different combinations. So our rate would be 6 times 1 over n. So in general, if we had 5, then it would be 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5. So in general, it can be shown that this value, which we can call n, the size of our sample, divided by 2, sorry, not divided by 2, but choose 2. So these parentheses, this annotation means n choose 2. How many combinations of 2 can I choose out of my sample of n? And this is equal to n minus 1 divided by 2. So if there are 2 individuals, then it's 2 times 1 over 2, so only 1 pair. If there are 3 individuals, then it's 3 times 2 over 2, 3 pairs. If it's 4 individuals, then it's 4 times 3 is 12 over 2, 6 pairs, which we just showed, and so forth. Okay, so in general then, what that means is, if we have n individuals in our sample, then we're going to have to wait, our waiting time is going to be equal to n choose 2 divided by n. We'll have to wait that many generations until things go back, until we get a coalescent event. Okay, so let's talk about what happens after our first coalescent event. So let's say by chance that these 2 individuals are the first pair to coalesce, and then that would mean these three individuals have not yet coalesced. So we expect, on average, this is going to happen at a rate of n choose 2 over n, which means on average we expect the inverse of that. We expect to wait n divided by n choose 2 generations. Okay, so then now if we're going to ask, so now we've figured out, we've gotten to our first coalescent event, and we can ask, okay, so if we're going to reconstruct our whole tree, now how long do we have to wait for our next one? So these 2 lineages, notice, now they only exist, they only have one ancestor from here back. So in effect now we're down 1 lineage. So we started with 5, and now we're down to 4. So that means in this preceding generation that we're going to also have a coalescent process, but now instead of it being n choose 2, now it's n minus 1 choose 2, again divided by n. So our waiting time we expect to be n divided by n minus 1 choose 2. And then on our previous generation we expect it to be to have this rate, and so to have this average waiting time. Okay, so let's look at these things. What does this all mean? And what's this going to mean? What's this going to mean for the shape of the tree? Okay, so it means that, so let's do this, let's just do it with 5. So over here, this would mean that the expected waiting time, this average waiting time, would be n divided by 5 times 4 divided by 2. We have 10 pairs. Then once we lose one, now it's n divided by 6. And then for the next one, it's n divided by 3. And then finally, for our last one, we have n minus 3, or 2 individuals choose 2. And so we're going to get n divided by little n choose 2. This is just 1. And so we get n. So what that means is that this, if we drew this to scale, that our first interval, this first interval back in time, is going to be 10 times as fast. The waiting time is going to be 1/10 as large as our last interval. So that actually, if we drew this to scale, this first one would be an inch, and then this next one would be about 1.5 inches. A little bit longer. And then the next one would be about twice that long. And then the final one would be 3 times that long. Right? Because if this length is n over 3, then we expect our last coalescent event with this last individual to be 3 times that long. 1, 2, 3. And so the point I want to make here is that, well, first here are the expectations, but the other point is that the tree looks really scrunched up at the bottom. I think probably if we guessed at what this would look like, the time between intervals, right? So this is our first interval, and then our second interval, and then our third interval, and then our fourth interval. These times, we would probably draw them as roughly equal. But because of this fact that when we have more individuals still in the sample, that we have more chances for pairs to coalesce. Because of that fact, in fact, we get this funny thing where we have a lot of, our deepest branches are very long, and the tips of our branches are very small.